In industrial pharmacy, evaporation is the process of removing bulk solvent from a solution to leave behind a concentrated, active medicinal residue. The engineering challenge lies in the scale. You must boil away thousands of liters of liquid without fracturing the delicate, heat-sensitive medicine suspended inside. The physics dictating this process comes down to a single thermodynamic formula, the heat transfer equation. Here, Q represents the total heat transferred, A is the available surface area, and U is the overall heat transfer coefficient, how efficiently thermal energy moves into the liquid. To scale production, engineers cannot simply increase the temperature, as that would incinerate the sensitive product. They must manipulate the other variables to keep the medicine intact. The pharmaceutical payload often consists of thermolabile drugs. These include sensitive biologicals like glycosides, alkaloids, and modern antibiotics. These specific chemical compounds are highly unstable at high temperatures, beginning to decompose at levels just below 100 degrees Celsius. Even at moderate temperatures, prolonged heating destroys the drug's active principles, rendering the entire batch useless. To scale safely, the industry must induce rapid boiling without relying on destructive raw heat. Saving the medicine requires redesigning the mechanical environment to change how boiling physically occurs. The simplest design is the hemispherical evaporating pan. A steam-jacketed exterior heats the contents, creating sluggish natural convection currents. Because these move slowly, a thick boundary layer forms along the inner wall, acting as an insulator, reducing the heat transfer coefficient and causing localized burning. In this open pan setup, the entire volume of liquid is heated simultaneously. This subjects the medicine to heat for unacceptably long periods. To solve this, engineers developed the short tube evaporator, also known as the Calandria. Instead of a single wide pan, the fluid is pushed through an internal nest of hundreds of small tubes, which drastically increases the available heating area. While the Calandria maximizes surface area, the fluid is still recirculating inside a large tank. The residence time remains dangerously long for sensitive modern biologicals. The obvious workaround for heat sensitivity is to lower the boiling point by attaching a vacuum pump. By reducing the pressure inside the vessel to 0.10 bars, aqueous solutions can boil at just 45 degrees Celsius. However, lowering the temperature triggers a hidden penalty, a massive spike in the solvent's viscosity. This chart plots sucrose solution viscosity against temperature. As temperature drops from 85 to 25 degrees, thickness rises exponentially. This thickness is problematic. The fluid's Reynolds number is inversely proportional to viscosity. As the liquid thickens, its internal mixing ability plummets. As a result, the chaotic mixing inside the evaporator stops. The fluid smooths out into distinct, slow-moving layers, a state known as streamline flow. The paradox is that streamline flow acts as an intense thermal insulator. The thick liquid touching the heated metal wall overheats, while the core of the liquid stays cold. Operating under a vacuum lowers the temperature, but without active fluid motion, that viscosity spike increases the risk of destroying the drug. To break the boundary layer in viscous fluids, engineers rely on the forced circulation evaporator. Instead of waiting for natural convection, a high-pressure mechanical pump drives the thick liquid through the heating tubes. In this design, the liquid is kept under such high pressure inside the tubes that it cannot boil while being heated. Only when the superheated liquid exits the tubes and enters the lower pressure main chamber does it flash into vapor. Mechanical force breaks the stagnant boundary layer and restores turbulent flow, allowing for the safe concentration of heat-sensitive extracts like insulin. For the most sensitive pharmaceutical products, engineers move away from bulk pools of liquid entirely, using the climbing film evaporator. Its architecture relies on narrow, steam-jacketed tubes that stretch up to 7 meters tall. This design marks a shift in logic. Instead of boiling a pool, engineers manipulate an incredibly thin layer of fluid. Cold or preheated liquor is injected into the bottom of the long tube. As heat transfers from the walls, boiling begins. As boiling intensifies, smaller bubbles merge into a single, massive pocket of gas, trapping a slug of liquid directly above it. The driving force is vapor-liquid friction. The expanding gas physically drags the fluid upward against gravity. This friction forces the liquid outward, spreading it into a thin film that races up the interior wall at high speed. Traveling at 6 to 7 meters per second, this velocity obliterates the boundary layer and maximizes the rate of heat transfer. By moving so fast, the total time the medicine spends exposed to heat drops from hours down to just 20 seconds. By maximizing heat transfer while minimizing exposure time, the climbing film evaporator reaches a highly efficient thermodynamic balance. Beyond the biological constraints of the medicine, industrial scale-up must address the economic cost of steam consumption. In a single-effect system, the latent heat absorbed by the newly created vapor is entirely wasted. Piping this high-energy vapor directly into a condenser pours valuable thermal energy away. To solve this, the industry uses multiple-effect evaporation as a primary thermodynamic recycling method. The mechanics are sequential. The waste vapor exiting the first evaporation tank is piped into the heating jacket of the second tank. Because the waste vapor is cooler than the original steam, it doesn't have enough heat to boil liquid at standard atmospheric pressure. Engineers drop the operating pressure in each subsequent tank. Lowering the pressure reduces the boiling point of the liquid, allowing the cooler vapor to induce boiling and maintain the process. This cascade allows pharmaceutical plants to evaporate up to 3 times the liquid using the same initial energy footprint. Every mechanical innovation in this process leads back to the heat transfer equation. Modern film evaporators maximize the values of U and A, while multi-effect vacuum setups optimize the delta T energy input. Industrial evaporation is the calculated manipulation of fluid dynamics to safely extract and preserve life-saving medicines at a global scale.